Dear friends and followers, welcome back to my channel and to an interesting video and a rare technical video about freezing fuel. We'll be talking about jet fuel characteristics, how to actually prevent fuel from freezing up, and a crash that resulted from freezing fuel a few years back. This is going to be a very cool topic, so let's get started.
Redwood 415, follow the mothership ahead on Apapa, monitor 1239. Good night.
Have a great night. Take care. Follow the mothership, Redwood.
Nowadays, when you board a plane, you expect to safely get from A to B and as fast as possible, please. But many passengers still worry about an engine or pressurization failure, but hardly anyone questions freezing fuel. Well, thankfully, no one really has to, primarily because of this part of equipment which is installed on most jet airliners, but I'll come back to that in a minute. Now, to simplify this video a little, we'll assume that car diesel has very similar characteristics as jet fuel. Now, flammable liquids such as diesel have 4 important temperature values. The auto ignition point, the temperature is so hot that the liquid will self-ignite. Then the much lower flash point, the temperature at which vapor would ignite if you add some flame to it. Then the cloud point at which the liquid slowly becomes cloudy, meaning particles are starting to freeze up. And last but not least, the so-called pour point at which diesel slowly starts to solidify into a crystalline state, giving it that wax or gel lookalike texture. Now, if your country is on this list right here, you might have heard of winter, alpine, or even Arctic diesel. Now, what's that? Now, let's say you were to live in Germany. These are the diesel cloud points you would be dealing with. Now, the summer diesel with a fairly high cloud point temperature. Now, if it were to get any colder, close to the pour point, the fuel would clog up your filter or injection system at those temperatures. Now, without knowing, as soon as the temperatures becomes lower towards winter, the petrol stations then fill up their tanks with winter diesel with a much lower cloud point of minus 20 degrees, so your car doesn't suddenly stop on the German Autobahn. That means the winter diesel is chemically treated to lower its cloud point, and there is a country which sells diesel with a cloud point of minus 50 degrees. Comment below if you think you know which country that is. It is not Canada, by the way. So how does this relate to jet airliners? Now, commercial jet fuel, or commonly known as kerosene, is split up into 3 major players. Jet A1, available outside of the US, Jet A, which is only available in the US, and the much more rare Jet B, which is primarily used in military aircraft and to be found in northern Canada, Alaska, and sometimes Russia, because of its low freezing point. Now, I said freezing point. The freezing point is similar to the cloud point. The jet fuel becomes cloudy, and if it gets any colder, approximately 6 degrees less than the freezing point, it solidifies to wax. Now, write this down, as this is a common question in your ATPL theory exam. What is the freezing point of Jet A1? Minus 47 degrees. So it is much lower than your average diesel fuel from the petrol station. And to all my American followers, yes, it is called a petrol station. I don't know why you call it a gas station. 99% of your cars run on a liquid, not on a gas. So as the wing tanks of the jet airliner are being refueled, the fuel commonly enters at outside air temperature. Now, let's say 20 degrees. Now, depending on where you are and how cold it is, fuel sometimes can be preheated before being filled into your wings. So as the plane then takes off and climbs to cruising level, let's say to flight level 360, the outside temperature plummets to a chilly minus 56.5 degrees and lower. So over time, the fuel will cool down as the jet fuel is in direct contact with the metal, for example, the wing, which is exposed to the freezing outside air temperature. And tests have shown that the cooling rate can vary from 3 degrees to 12 degrees per hour in severe conditions. So let's quickly look into how fuel temperature is being measured. Now, on the Boeing 747, the fuel tank temperature sensor is located in main tank 1. Do you have any idea why it's located specifically in that tank? Now, as the outer part of the wing is much thinner, it has a low surface to volume ratio, meaning the fuel tank profits less from the thermal friction of overpassing air than the tank near the wing root. Plus, their volume is much smaller, so a small pond freezes up much quicker than a large lake. Now, another very important indicator to monitor the fuel temperature is the total air temperature gauge right here. Now, what is the total air temperature? Now, the very simple answer is the airplane's surface temperature, which generally is warmer than the SAT, the static air temperature. Now, the TAT is the result of the static air temperature and the Mach number. You can very often see its probe placed at the forward part of the fuselage. So as a pilot, you are advised to monitor the fuel temperature gauge from time to time. Now, other than that, in case the fuel temperature reaches minus 37 degrees, on the 747, the ICAS message fuel temp low is triggered. Now, why is minus 37 degrees the trigger for that warning? Minus 37 degrees is 3 degrees prior freezing point of Jet A, which is only sold in the States, and Boeing being an American-based company, they want you to take action once that warning pops up before the fuel gets any colder. So what do you do as a pilot if that message appears? Now, funny enough, you would have to check the fuel receipt where you have last refueled your plane, Jet A1 in your tanks, meaning your freezing point is at minus 47 degrees. So at that point, nothing really to worry, but you would have to time the decrease in fuel temperature and compare it to the remaining flight time to not make the situation any worse. Now, a very important statement here. But what if the plane was recently fueled in the States with Jet A and then mixed with some Jet A1 fuel from Europe? You would have to consider the higher freezing point of minus 40 degrees for the time being. Boeing recommends only after 3 consecutive Jet A1 refueling stops you could use the lower freezing point of minus 47 degrees. Makes sense, right? So you see, there is a potential risk, especially on long flights routing near the polar areas, that fuel freezes or turns into a sluggish, waxy jello state, clogging up the fuel lines, decreasing the engine output, or even worse, letting the engine flame out. So what can you practically do as a pilot to avoid your fuel from freezing up? Now, the in-flight procedure recommends primarily to closely monitor the indicated fuel temperature and the total air temperature, as their difference is your main indicator for further actions. Step 1, and you might think I'm joking, increase your speed. Yes, increasing your airspeed will have an impact on your fuel temperature. Now, but how? Flight tests have shown that only 0.01 Mach increase in speed will raise the total air temperature, respective the fuel temperature, by 0.5 to 0.7 degrees. I personally find that quite impressive, that just that little increase in airspeed creates so much more air friction and so raises the total air temperature, fuel temperature. But keep in mind, higher airspeed, more fuel burn per hour. The second option would be to descend to a warmer air mass. Now, the manual recommends 3,000 to 5,000 feet below the optimum altitude. Optimum altitude, the best aircraft cruise altitude for a given weight and corresponding air temperature. Again, as flight tests have shown, descending 4,000 feet in standard conditions corresponds to 8 degrees in total air temperature difference, but again, lower level, higher fuel burn. The third option would be to divert to a warmer air mass. Now, for instance, if you were to be flying close to a jet stream, it often depends if you are on the warm or cold side of the jet stream. And secondly, the closer you are to the core, the colder it can be, depending where the jet stream is coming from and moving to. Now, let's say you took all preventive measures from fuel waxing up, but there is still one more chance of the fuel to freeze up. Jet fuel itself isn't entirely all fuel. There are tiny parts of water in kerosene. And water, as we all know, freezes at temperatures below 0 degrees. So in order to not clog your fuel lines towards the engine combustion chamber, airplane engineers have come up with a very clever win-win solution. They have put a so-called fuel-to-oil heat exchanger in place. The engine oil of jet turbines gets pretty hot, and as discussed, fuel gets pretty cold. So why not let the hot oil run through a set of pipes which are adjacent to cold fuel lines? So the oil temperature decreases while the fuel temperature rises. If that ain't clever, I don't know what is. Side note, very often the engineers place warmer hydraulic lines and bleed air pipes along the fuel tanks to radiate their heat and warm the fuel. Also an option is to pump the fuel into the center tanks, as the fuselage very often is warmer than the wings as it is less exposed to the cold airflow. A sad side note, the mentioned fuel-to-oil heat exchanger was the cause for the unfortunate landing of British Airways Flight 38 at Heathrow in January 2008. Now, the route from Beijing towards Europe took the plane through air masses as cold as minus 74 degrees, leading to a lot of ice buildup in the fuel lines. Now, as the plane started its descent, only little thrust was used, but upon final approach, the pilots added power as usual, which suddenly released the ice in the fuel lines, blocking the fuel-to-oil heat exchanger inlet. The blockage caused an immediate thrust loss on both engines, and at 500 feet the plane glided towards the runway. Lacking in power, it landed short of the runway and ripped off the landing gear. Luckily, all 152 passengers and crew survived. Following that accident, the fuel-to-oil heat exchanger had to be redesigned that it could cope with large chunks of ice at its inlet. I think the message of today's video is never take anything for granted on an airplane. Know what you're doing, know your systems, and stay alert. That's it for today. Thank you very much for your time. Check out my new t-shirts design just above the description box. If you are a Boeing or Airbus lover, you definitely want to get more of my new shirts. And as always, hit that subscribe button and activate the notification bell so you won't miss out upcoming videos. And don't forget, a good pilot is always learning. See you next week. Wishing you all the best, your Captain Joe.